Hello friends, welcome to all in my YouTube channel all about civil engineering by Pravin PM. Today I am delivering audio video lecture on strength of materials, one of the most important section for competitive examination like GATE, IAS, SSC JE, IAS, IPS, IES, RRB and many more other competitive examinations. But as far as GATE 2021 is concerned, this is the very important topic. Today we will see basic concepts of strength of materials and solving the some numericals. These video lectures is also useful for second year civil engineering student for the subject strength of materials. Now we will directly go for the subject, and here stress and strain. First concept is stress and strain. What is meant by stress? Stress is denoted by sigma, and sigma is stress, sigma is A. Suppose this is the material and the force is applied, so force is applied on both the side. P is a force subjected to external force, resisting force up within the component, and the whenever we apply any force on the any material, some resistance, internal resistance is developed in the material. That internal resistance per unit area acting on a material is called as the stress at that point. So therefore stress is equal to P upon A. P is the force and A is the area upon which the force is acting. Then P is expressed in Newton and A is original area in square meters. The stress sigma will be expressed in Newton per meter square. This is called a Pascal. Newton per meter square is also called as the Pascal. So there is some other changes we can convert. So 1 kilopascal is equal to 10 raised to 3 Pascal, that is 10 raised to 3 Newton per meter square. 1 MPa, that is megapascal. Megapascal is 10 raised to 6 Pascal, that is 10 raised to 6 Newton per meter square, that is equal to 1 Newton per mm square. And 1 GPa, gigapascal, is equal to 10 raised to 9 Pascal, that is 10 raised to 9 Newton per meter square. Now let us take an example, like rod of 10 mm by 10 mm cross section is carrying an axial tensile load 10 kilonewton. In this rod, tensile stress developed is given by sigma T is equal to P upon A, 10 kilonewton divided by 10 into 10, that is 10 into 10 raised to 3 Newton divided by 100, that is 100 Newton per mm square, that is 100 MPa. So when the forces acting on any member opposite, both the side opposite direction, these are the tensile forces, create tension, and if the forces acting in this fashion, these are create the compression. The resultant of the internal forces for an axially loaded member is normal to a section cut perpendicular to the member axis. The force intensity on the shown section is defined as the normal stress, that is the force intensity delta A. Small, if you consider small area, that is delta A. So this sigma is equal to limit delta A tends to 0, delta F upon delta A. So is equal to sigma average is equal to P by A. If we take its limit integration, we will get this. Then tensile stress sigma T. If sigma is greater than 0, the stress is tensile. The fiber of the component tend to elongate due to external force. So this fiber will elongate due to external force. So that is the tensile. Now compressive sigma C for compression. If sigma is less than 0, the stress is compressive. So this is the compressive force acting, and this will create the reduction in the length of member. Then shear stress is the if stress is acting in this fashion. So when forces are transmitted from one part of body to other, the stresses developed in the plane parallel to the applied force are the shear stress. Shear stress acts parallel to the plane of interest. Force P is applied transversely to the member AB as shown. The corresponding internal forces act in the plane of C is called a shearing. So shear stress will be like this. We are showing in this fashion. This is the shear stress, and it is denoted by tau. Tau is the P divided by area, but area is this area. This area we need to take. Then we will go for the strain. Strain is nothing but it is the displacement per unit length is known as strain. It is dimensionless quantity. Why it is dimensionless, that we will see. Suppose strain, what is meant by strain? Strain means, suppose this is the original member. If after application of load, the member length will be increased, delta L. So delta L divided by L, 0, original length, change in length divided by original length is equal to elongation, that is the strain, is equal to, that is the strain, that is ET, it is tensile strain, is equal to delta L divided by L0. It is engineering strain or conventional strain. Here we divide the elongation to original length, not actual length, L0 plus delta L. See, where this is the engineering strain or conventional strain, because here dividend is L0, original length, we are taking only original length. And so take the example, let us take an example. If a rod 100 mm is original length, when we apply an axial load of 10 kilonewton, the final length of the rod after application of the load is 100.1 millimeter. So in this rod, tensile strain developed is given by ET is equal to delta L divided by L0. It is L minus L0 divided by L0. 100.1 mm minus 100 divided by 100. It is 0.1 divided by 100. That is 0.001 tensile. As the unit of both numerator and denominator is same, so this quantity is dimensionless. Now compressive strain. Compressive strain, if the applied force is compressive, then the reduction of length per unit length is known as the compression. That is negative. See, compression creates the negative effect. It will reduce its length of that member, and tension will increase the length. So tensile strain will be positive, compressive strain will be negative. Then shear strain. So shear strain will be like this. When a force P is applied tangentially to the element shown in figure, in this fashion, if we applied, it will create change delta in this fashion. So this length will be changed, but this length remains same. This here, this length also change. Its edge displacement is dotted line, where delta is the lateral displacement of the upper face. So there will be a lateral displacement. This is lateral displacement, and shear displacement is like this. So delta is the lateral displacement, the upper face of the element relative to the lower face of the L is the distance between these forces. Therefore the shear strain is denoted in this by is equal to delta divided by L. So delta divided by L, L is this length of bottom line, and this is the change in length. So change in length of top line divided by bottom line, that is the shear strain. Let us take example. So this will be the example. Then true stress and true strain. So already we have studied engineering stress and strain. Now true stress. The true stress is defined as the ratio of load to the cross sectional area at any instant. So delta T is equal to load upon instantaneous area is equal to sigma divided by 1 plus, this is the epsilon, that is the strain. So where sigma and E is the engineering stress and engineering strain respectively. Then true strain ET is equal to integration L0 to L delta L divided by L is equal to integration L divided by L0 is equal to integration 1 plus epsilon is equal to integration A0 divided by A is equal to 2 into IN D0 divided by D, or engineering strain E is equal to E raised to ET minus 1. So the volume of the specimen is assumed to be constant during plastic deformation. So A0 L0 is equal to A into L. It is valid till the neck formation. As you know, comparison of engineering and true strain shows here comparison. The true stress strain curve is also known as flow curve. True stress strain curve gives a true indication of deformation characteristics because it is based on the instantaneous dimension of the specimen. So this is the true stress strain curve, this is the corrected for necking, and this is the curve for engineering stress. So this will be the maximum load here, and this will be the fracture as far as engineering stress is concerned. As far as true stress strain is concerned, there will be no fracture or fracture after some point. So here on x axis will take strain, y axis will take stress. If anybody want detailed information about this stress strain curve for engineering stress strain curve, so you just refer one video I have posted earlier to this channel only regarding the stress strain relationship. And then if anybody want in detail these concepts, so join my playlist of this channel for audio video lecture series for strength of material subject, which I have taken for second year engineering student. So this is whatever we are doing for GATE. So the flow curve of many metal in the region of uniform plastic deformation can be expressed by the simple power law. Sigma T is equal to K into epsilon T raised to N, where K is the strength coefficient, N is the strain hardening exponent, N is 0 for perfectly plastic solid, N is equal to 1 for elastic solid. For most metals, N is greater than 0.1 and less than 0.5. So here relation between ultimate tensile strength and true stress at maximum load. The ultimate tensile strength sigma u is equal to P max divided by A0. So here is the member, area is A0, length is L0, force P is applied tensile force, axially loaded member. So it will create effect, change in area will be A, change in length will be L. So the true stress at maximum load sigma u upon T is equal to P max divided by A, and true strain at maximum load sigma T is equal to integration A0 divided by A, or A0 divided by A is equal to E raised to epsilon T. Eliminating P max, we get sigma u true is equal to P max divided by A is equal to P max divided by A0 into A0 divided by A, which is equal to sigma u into E raised to epsilon T, that is the true strain, where P max is equal to maximum force and A0 is original cross sectional area, A is instantaneous cross sectional area, I mean after change, after force. Let us take two examples. So this is the one example. One, only elongation, no neck formation. In the tension test of rod shown, initially it was area A0 is equal to 50 mm square and L0 is equal to 100 mm. After the application of load, its A is equal to 40 mm square and L is equal to 125 mm square. As see, if there is increase in length, so area will be decreased. So area will be decreased. Determine the true strain using changes in both length and area. Answer: first of all, we have to check that does the member forms neck or not. For that, check A0 L0 is equal to A into L. Is we satisfy this equation or not? So 50 into 100 is equal to 40 into 125. So no neck formation is there. Therefore, true strain is equal to epsilon T is equal to integration L0 to L dl by L is equal to integration 125 by 100 is equal to 0.223. So is epsilon T, that is the true strain, is equal to 0.223. As strain is dimensionless, so no dimension. So elongation with neck formation. If neck formation is there like this, if neck formation is there, there should be a breakage, there should be a break point. So a ductile material is tested such as necking occurs, then the final gauge length is L is equal to 140 mm and the final minimum cross sectional area is A is 35 mm square. So minimum cross section area is 35 mm cross section. So though the rod shown initially it was A0 50 mm square and L0 100 mm, determine the true strain using changes in both length and area. Answer: first of all, we check this. If we not 50 into 100 5000 and L is equal to 35 into 140 4200 mm cube. So neck formation is there. Here A0 L0 is greater than AL. Therefore, true strain is equal to in A0 upon A is equal to 50 upon 35 is equal to 0.357, but not epsilon T is equal to in integration 140 divided by 100 is equal to 0.336 is wrong. 357 is correct because neck formation is there. Then according to Hooke's law, now we will say first different laws. Hooke's law. What Hooke's law says? Hooke's law says the stress is directly proportional to the strain, that is the normal stress sigma is directly proportional to the normal strain epsilon, and shearing stress tau is directly proportional to shearing strain. So sigma is equal to E divided by E, and tau is equal to G divided by this. So G into this. So E is the modulus of elasticity and G is the shear modulus of elasticity. E is the capital E is the modulus of elasticity and G is the shear modulus of elasticity or modulus of rigidity. Now volumetric strain epsilon V. Volumetric strain is equal to a relationship similar to that of length changes hold for 3-dimension volume changes. For volumetric strain, sigma epsilon V is equal to, the relationship is epsilon V is equal to V minus V0 divided by V0, or sigma V is equal to delta V divided by V0 is equal to P by K. So where V is the final area, V0 is the original volume, final volume, V0 is the original volume, and delta V is the change in volume. Volumetric strain is the ratio of values with the same units, so it is also dimensionless quantity. So delta V divided by V is equal to volumetric strain is equal to epsilon x, epsilon y, epsilon z is equal to epsilon 1, 2, 3. So epsilon x in x direction, in y direction, and z direction. We just need to addition. We need to calculate separately. In x direction, epsilon x is equal to delta V x divided by V, and same way we need to calculate dilation. The hydrostatic component of the total stress contributes to the deformation by changing the area or volume in 3-dimension of an object. Area or volume change is called dilation and is positive or negative as the volume increases or decreases respectively. E is equal to rho divided by K, where rho is equal to is the pressure. Rho is equal to pressure. Whatever changes in the area or volume in 3-dimensional object, that is called as the dilation. So Young's modulus or modulus of elasticity is equal to PL by A into sigma, that is sigma divided by epsilon. So P by A is sigma, delta L by L is epsilon. So modulus of rigidity or shear modulus of elasticity, G is equal to tau by shear strain, which is equal to PL divided by A sigma. Bulk modulus or volumetric modulus of elasticity, K. So K is volume modulus of elasticity. So shear modulus of elasticity G, capital G, Young's modulus of elasticity E, and bulk modulus or volume modulus of elasticity K is equal to delta P, that is the pressure, delta P divided by delta V by V, that is equal to delta rho P divided by delta R divided by R. So if anybody want any detail about this, so you can join my online classes for or online lectures for strength of material subject. So there I am explaining in detail everything. So then here relationship between the elastic constant E, G, K and mu. So E is equal to 2G into 1 plus mu is equal to 3K into 1 minus 2 mu is equal to 9 kg divided by 3K plus G. This is a very important formula. You should keep in mind. So where K is the bulk modulus, mu is the Poisson ratio, E is the Young's modulus, G is the modulus of rigidity. So for linearly elastic, isotropic and homogeneous material, the number of elastic constant required to relate stress and strain is 2. That is, any 2 of the 4 must be known. If the material is non-isotropic, that is anisotropic, then the elastic moduli will vary with additional stresses appearing since there is coupling between shear stress and normal stresses for an anisotropic materials. Now let us take example. So now Poisson's ratio. So what is the Poisson's ratio? Poisson's ratio is transverse strain or lateral strain divided by longitudinal strain. So whenever we apply load to the rod, so its area is this, initial shape is this. After applying tensile load, the area will be changed. So lateral strain or transverse strain to the longitudinal strain is called as the Poisson's ratio, that is the mu, that is the minus epsilon y divided by epsilon x under unidirectional stress in x direction. So it is the ratio of lateral strain to the longitudinal strain, as lateral strain is negative in this case. So that's why it is the negative. The theory of isotropic elasticity allows Poisson ratio in the range of 1 to 1/2. So Poisson's ratio in various material is given here. So material steel Poisson ratio is 0.25 to 0.33. Ci cast iron material, it is 0.23 to 0.27. As far as concrete is concerned, Poisson's ratio is 0.2, and as far as rubber, Poisson's ratio is 0.48 to 0.5. For cork, it is nearly 0, and as far as novel foam is concerned, it's a negative value. We use cork in a bottle as the cork easily inserted and removed. It also withstands the pressure from within the bottle. Cork with a Poisson ratio of nearly 0 is ideal in this application. So cork is a ideal material where Poisson's ratio is 0 because lateral strain and longitudinal strain will be 0. So no change in dimension after application of force. That is the cork material. So now biaxial stretching of sheet. Epsilon 1 is equal to integration L F1 divided by L01, and epsilon 2 is equal to integration L F2 divided by epsilon L02. LO is equal to original length, LF is equal to final length. So final thickness TF is equal to initial thickness T0 divided by e raised to epsilon 1 into e raised to epsilon 2. So for detail of this formula, you just refer my online lectures or of this subject. Then elongation. Elongation is the prismatic bar loaded in a tension by axial forces. If force is loaded L, so this will be increase in length delta. So for prismatic bar loaded in tension by an axial force, the elongation of the bar can be determined as delta is equal to PL divided by A. Is P is the force, L is the length, original length, A is the area, and E is the modulus of elasticity. Now this is the example. Then elongation of composite body. So elongation of composite body bar of varying cross sectional area A1 A2 to AN of length L1 L2 to Ln respectively is delta is equal to P divided by E. This is the common. So length L1 divided by A1 plus L2 by A2 plus L3 by A2 up to Ln by An. So we'll see this by example. This is the first. Area is 300 mm square, length is 300 mm, area is 40 mm square. Here length is 500 mm, area is 20 mm square. Here for this member area is 30 mm square and length is 200 mm. So force applied is 1000 Newton tensile force. So given load P is 1000 Newton, E is value is given 200 GPa. So area A1 is equal to 40, A2 is equal to, so area given, length are given, E is equal to given. So we convert GPa, this is given in gigapascal, that is 200 into 10 raised to 9 Newton per meter square, which is equal to 200 into 10 raised to 3 Newton per mm square. As this is in mm square, so we need to area in mm square. So we put the values in earlier formula, we will get the answer. Now elongation of tapered body. So formula for elongation of tapered body is elongation of tapering rod of length L due to load P at the end is equal to delta is equal to 4PL divided by pi capital E D1 into D2. So where D1 and D2 are the diameters of the smaller and larger end for tapering rod. So you may remember this is the way sigma is equal to, delta is equal to, that is the elongation is equal to PL divided by E into bracket pi by 4 D1 D2, pi by 4 D1 D2. So that is PL divided by E into A equal. So this is the example. So we need to memorize these equations. Then so this is here. So D1 D2 force P applied, dx is the x, this is the length L. For this explanation of this formula or derivation of formula, you just refer the audio video lectures on strength of material subject. So dx by 2 is equal to d1 by 2 into x divided by L into d2 by 2 minus d1 by 2, or dx is equal to d1 plus x by L into d2 by d1 is equal to d1 into 1 plus kx, where k is equal to d2 minus d1 by L into 1 upon d1. So now taking small strip of diameter dx and length dx at section xx, elongation of this section dx length d delta is equal to PL by AE is equal to P into dx divided by pi by 4 dx d square x into E is equal to 4p into dx divided by pi into bracket d1 into bracket 1 plus kx into bracket square is into E. Therefore, total elongation of the taper bar is equal to delta is equal to integration d delta, which is equal to integration x tends to 0 to L 4p dx divided by pi into E into d1 square into bracket 1 plus kx bracket square, which is equal to 4 PL divided by pi E d1 d2. Case 1, where d2 is equal to 2d1. If d2 is equal to 2d1, elongation delta L is equal to 4 PL divided by pi E d1 into 2 d1. So do 2 PL divided by pi E d1 square. Case 2, where we use mean diameter, dm is equal to d1 plus d2 divided by 2. So d1 plus 2 d1 divided by 2 is equal to 3 by 2 d1. Elongation of such bar is equal to PL divided by AE, which is equal to PL divided by pi by 4 3 by 2 d1 square into E, that is 16 PL by 9 pi E d1 square. Extension of taper bar divided by extension of uniform bar. So in this fashion. Now elongation of body due to its self weight. So elongation of uniform rod length L due to its self weight W is equal to PL by AE to WL by 2AE. The deformation of bar under its own weight as compared to that when subjected to a direct axial load equal to its own weight will be half. Now total extension produced in rod L due to its own weight omega per with length per unit length delta is equal to omega L square divided by 2 EA. Elongation of conical bar due to its self weight is equal to delta is equal to rho g into L square divided by sigma E 6E, that is the WL divided by 2 A max into E. So here structural members or machines must be designed such that the working stresses are less than ultimate strength of material. So working stress sigma W is equal to sigma Y divided by N is equal to 1.5 to 2, sigma ultimate divided by N1 is equal to 2 to 3. These are the factor of safety. N is the factor of safety. Sigma P divided by N is equal to sigma P divided by proof stress. Factor of safety N is equal to sigma Y or sigma P or sigma ultimate divided by sigma W. Sigma W is working stress. Sigma Y, sigma P and sigma ultimate, they are the stresses: normal stress, proof stress, ultimate stress. Then thermal or temperature strain, stress and strain. When a material undergoes changes in a temperature, it either elongates or contracts. If there are changes in temperature, the material may be elongates or contracts. So if the elongation is contracted, is not restricted, that is free, then the material does not experience any stress despite the fact that it undergoes a strain. The strain due to temperature change is called a thermal strain, and it is expressed in epsilon is equal to alpha into delta T, where alpha is the coefficient of thermal expansion, material property, and delta T is the change in temperature. The free expansion or contraction of material when restrained induces stress in the material, and it is referred as the thermal stress. So see, listen. So one time the elongation or contraction is not restricted, it is a free, and expansion or contraction is restricted or restrained, then that is the change in stress is called the thermal stress and change in strain is called as the thermal strain. So temperature stress is equal to alpha E into delta D, where E is the modulus of elasticity. The thermal stress produces the same effect in the material similar to that of mechanical stress. A compressive stress will produce in the material with increase in temperature, and the stress developed is tensile stress with decrease in temperature. So if temperature is decreased, the stress developed is tensile. If temperature is increased, the stress developed is compressive. Now this is the example. Now thermal stress on brass and mild steel. So thermal stress on brass and mild steel. For details of derivation or details, you just refer the audio video lectures on strength of material subject. There I am explaining where in detail each and every point. So a brass rod placed within a steel tube of exactly same length. So brass rod is middle and steel up at top and bottom we have placed the steel. So the assembly is making in such a way that elongation of combination will be same. To calculate the stress induced in the brass rod steel tube when the combination is raised by T0 degree centigrade, then following analogy have to do. Original bar before heating. So this will be the length. Expanded position if members are allowed to expand freely and independently after heating. Independently, there is no restriction. So this will be the expansion of bar. Then third, expanded position of the compound bar, that is the final position after heating. After heating, this is the final position. So compatibility equation, delta is equal to delta ST plus delta SF is equal to delta BT minus delta BF. Assumption, L is equal to LS is equal to LB. Alpha B is greater than alpha S. Steel tension, brass compression. Equilibrium equation, sigma S into AS is equal to sigma B into AB. So where delta is the expansion of compound bar is equal to AD in the above figure. Then sigma delta ST is the free expansion of the steel tube due to temperature rise T degree centigrade is equal to alpha S L into T is equal to AB in the above figure. Delta ST is equal to expansion of steel tube due to internal force developed by unequal expansion is equal to BD in the above figure. Delta BT is equal to free expansion of the brass rod due to temperature rise T degree centigrade, which is equal to alpha B into L into T, which is equal to AC in the above figure. Delta BT is equal to compression of the brass rod due to the internal force developed by the unequal expansion, which is equal to BD in the above. And in equilibrium equation, tensile force in the steel tube is equal to compressive force in the brass rod, that is sigma S tensile stress developed in the steel tube, sigma B compressive stress developed in the brass rod, AS cross sectional area of steel tube, AB cross sectional area of brass rod. Now maximum stress and elongation due to rotation, if the rotation is like this bar. So sigma max is equal to rho W square divided by L square divided by 8, and delta L, that is the strain, P rho into the omega square into L square divided by 12 E, where E is the modulus of elasticity, where sigma max is equal to P omega square into L square divided by 2, and delta L is equal to P into omega square into L cube divided by 3E. For remember, you will get 2 by multiplying by 4 of 1. You will get 2 by multiplying by 4 of 1. Here we multiplied 4, will get this second equation. So creep, what is meant by creep? So creep, when a member is subjected to constant load over a long period of time, it undergoes slow permanent deformation, and this permanent deformation is called as the creep. So permanent deformation means after removal of load or force, the member will not get returned to its position. So this is called as the creep. Usually at elevated temperature, creep is high. So the material have its own different melting point. Each will creep when the homogeneous temperature is greater than 0.5. Homologous temperature is equal to testing temperature divided by melting temperature, which is greater than 0.5. That is, the testing temperature should be greater than melting temperature. So melting temperature should be the half of testing temperature. A typical creep curve shown in the three distinct stages. Here typical creeping curve. Here time and here strain is given on, shown on y axis. So epsilon alpha, the constant creep rate in the second step, represents the creep rate of the material. This is primary creep, secondary creep, and this is tertiary creep, and here is the fracture of material. So primary creep is a period of transient creep. The creep resistance of material increases due to material deformation. Creep resistance increases. Here secondary creep provides a nearly constant creep rate. The average value of creep rate during this period is called the minimum creep rate. A stage balance between competing strain hardening and recovery of the material. Strain hardening and recovery of material. So d epsilon divided by d T is equal to minimum creep rate. Now tertiary creep. It shows a rapid increase in the creep rate due to effectively reduced cross-sectional area of the specimen, leading to creep rupture or failure. In this stage, irregular cracking and or formation of voids and cavities occur. Creep rate is equal to C1 into sigma raised to C2. Creep strain at any time is equal to 0 time strain intercept plus creep rate into time. So epsilon 0 plus C1 sigma raised to C2 into T. So where C1 and C2 are the constant and sigma is the stress. Now if load P is applied suddenly to a bar, then stress and strain induced will be double than those obtained by an equal load applied gradually. If we applied load gradually, we will get the values. Then if we applied load suddenly, then there will be stress and induced will be double. Now stress produced by load P in falling from height h, sigma d is equal to sigma into 1 plus square root of 1 plus 2h divided by epsilon L bracket into sigma. Sigma is the stress, normal stress. E epsilon being stress and strain produced by static load P and L, A divided by P epsilon, that is the strain, is equal to A divided by P into bracket 1 plus square root of 1 plus 2A into E into H divided by PL. So H is the height, A is the area, P is the load force, L is the length, and E is the capital E is the modulus of elasticity of that material. Now load shared by material of compound bar made up of bars X and Y due to load W. Px is equal to W into Ax divided by, into Ex divided by Ax Ex plus Ay Ey. Py is equal to W into Ay Ey divided by Ax Ex plus Ay Ey. So elongation of compound bar sigma is equal to delta is equal to PL divided by A1 Ax Ex plus Ay Ey. So now this is the tension test, and this is what the stress strain curve. So here strain, here stress. So plastic strain, elastic strain. So elastic deformation, this is plastic deformation, this is neck formation, here fracture, here ultimate tensile strength, here yield strength. Young's modulus is equal to slope is equal to stress divided by strain. So here uniform plastic deformation, and in this section non-uniform plastic deformation, means here this is the elastic deformation, here uniform plastic deformation, and here non-uniform plastic. So here the fracture happens after neck formation. There is no chances of returning this material in their original shape. So after necking is the ultimate tensile stress. So here fracture occurs. This is the L0. This is the first point, yield strength point. This is the neck formation, and this is the fracture one. So this is the stress strain curve. So now true elastic limit based on micro strain measurement at strain an order of 2 into 10 raised to minus 6, very low value, and is related to the motion of few hundred dislocations. Proportional limit is the highest stress at which stress is directly proportional to the strain. Elastic limit is the greatest stress the material can withstand without any measurable permanent strain after unloading. Elastic limit greater than proportional limit. Now yield strength is the stress required to produce a small specific amount of deformation. So that is the yield strength. So epsilon is 0.002 or 0.001. So extension, and this is the load. This is the offset yield. Now tensile strength or ultimate tensile strength, sigma u is the maximum load Pmax divided by original cross sectional area A0. Percentage elongation is equal to LF minus L0 divided by L0. Reduction of area Q is equal to, small q is equal to A0 minus AF divided by A0. So now stress strain responses. So linear elastic, the stress strain curve is like this. Linear elastic but perfectly plastic, stress strain curve is like this. Linear elastic hardening plastic, stress strain curve is like this. And linear elastic hardening plasticity with unloading, so this will happen in this fashion. So elastic strain and plastic strain. So the strain present in the material after unloading is called a residual strain or plastic strain, and the strain disappears during unloading is termed as elastic strain. So sigma is equal to E total, epsilon total strain into capital E minus epsilon plastic. Epsilon E into E is equal to E plastic, epsilon plastic into E. Carefully observe the following figures and understand which one is the elastic strain. So this is the residual strain, this is elastic strain, this is elastic strain, and this is elastic strain, and this is residual strain. This is residual strain. Residual strain is the strain present in the material after unloading, and elastic strain, the strain disappears during unloading, that is the elastic strain or recoverable strain. So this is the example. So elasticity. So what is elasticity? This is the property of material to regain its original shape after deformation when external force are removed. So this is the rubber may be the example. Then plasticity, when the stress is in the material exceeds the elastic limit, the material enters into plastic phase where the strain can no longer be completely removed. Under plastic condition, material ideally deform without any increase in stress. So in plastic condition, plasticity, the stress will not increase but strain will increase, go on increasing. Strain will go on increasing. So change in length, so deformation will be increased, but their stress remains same. Then strain hardening. Strain hardening, if the material is reloaded from point C, it will follow the previous unloading path of line CB, become its new elastic region with elastic limit defined by point B. Through the new elastic region CB resembles that the initial elastic region OA, the internal structure of the material in the new state has changed. The change in the microstructure of the material is clear from the fact that ductility of the material has come down to the strain hardening. When the material is reloaded, it follows the same path as that of virgin material and fails on reaching the ultimate strength, which remains unaltered due to intermediate loading and unloading process, that is the strain hardening. Means at this point after unloading, if we loaded this member again, then same thing will happen, same curve will be there. So first elastic limit, plastic limit, and then a breaking point, and then fracture. Then stress reversal and stress strain hysteresis loop. So that we will see in the next part. So now here after this there are question papers, questions asked in the previous GATE, IS examinations. Here I have shown only the questions. You just try it. If not, then ask me. I will give you the solution answer for this. So this will be the questions I have clear. Now stress in a bar due to self weight. So same thing, questions will be asked. So these are the questions I have. That is the question bank. You can say question bank from the previous 20 years question papers of GATE, IS, IPS, IAS examinations. So I have prepared that question bank. So answers are also given, but solution is not given. You just try it. If not, I will provide your solution. So thank you for watching the audio video lecture. If you like it, please do share it and subscribe the channel for more such fruitful video. Same video you will get in the Marathi language in my another YouTube channel, that is MPSC UPSC online PM Academy channel. And as far as detailed lectures on strength of material subject concerned, you just follow my channel playlist on audio video lectures on subject strength of materials. There I am explaining all the topic in detail, everything in detail, every derivation in detail. Thank you for watching the video. If you like it, please do share it and subscribe the channel. We'll meet next for next audio video lecture in next session or next subject, or you can say next branch or next point from the GATE syllabus. So best of luck for you for your GATE examination study. Thank you.